In the last video, we saw that quantum numbers could be used to define orbitals, probability wave functions describing where electrons can exist in an atom. In this video, we're going to look at the shapes of those atomic orbitals. So we started off by talking about the hydrogen atom, and we built up the Bohr model of the atom in which we were able to calculate the energy levels of all of the different orbitals. And the hydrogen atom is spherical, and the orbitals that are predicted from Bohr's formulas always wind up being spherical as well. Well, as it turns out, all of the orbitals that combine to make any particular subshell in an atom also combine to make a shape that is spherical. And so you will wind up potentially with 3p orbitals that point in different directions, but when they all stack on top of each other, you wind up with something that's effectively spherical. As I mentioned when I introduced the angular momentum quantum number in the last video, the shapes of the orbitals are actually dictated by their nodes. And as it turns out, there's two types of nodes that can appear in atomic orbitals. And the number of nodes increases as the principal quantum number increases. Every atomic orbital has one fewer node than its principal quantum number. So since the energy gets higher as the principal quantum number gets higher, also the number of nodes gets higher as the principal quantum number gets higher. And it will be important in Chem 2000, this concept that energy is actually related to number of nodes. Now, we don't see all of those nodes initially if we just look at a surface representation of the shape of the orbital. The nodes that we are able to see if we just draw an outline of the orbital, those are oftentimes referred to as planar nodes, and the number of planar nodes is equal to that angular momentum quantum number. The other nodes in your atomic orbitals are what we refer to as radial nodes, and they are nested inside the atomic orbital. We'll see what those look like in a little bit. So we'll start by talking about the simplest shape of orbital, the s orbital. The s orbital looks like a sphere, and as such, there are no planar nodes, which is consistent with the angular momentum quantum number being 0. You can see in front of you some mathematical descriptions of an s orbital and also a couple of different pictures of the s orbital. Now, I mentioned the potential for radial nodes. Radial nodes are essentially concentric shapes within the outermost shape. So in an s orbital, and we have the nucleus right in the middle here where I'm putting a red dot in each of those pictures. The 1s orbital has n equals 1 and therefore no nodes at all. And so it just looks like all the pictures we've looked at so far. The 2s orbital, so the s orbital for which n equals 2, should have n minus 1 node. It should have one fewer node than the principal quantum number. So therefore, there has to be one node there, but it's a sphere. So there's no planar node there. The node instead is between an inner sphere that's very, very tiny. And so there's a very small probability that the electron is extremely close to the nucleus. And then there's this much larger outer region here, which is where most of the probability is that the electron is in this outermost space. And so that border, that white region that you're seeing between the yellow and the blue, that's the node. There is one radius at which there is exactly 0 probability that the electron exists. And when we go up to the 3s orbital, the orbital for which n equals 3, we must have 2 nodes because, again, we should have one fewer node than our principal quantum number. And so you can see that there are 2 white lines here that I'm now drawing over top of in red. And those are the spaces where there is no electron density whatsoever in that orbital. And those are your radial nodes. And you see, again, a shift in phase. Every time you cross a node of any type in an atomic orbital, you always switch phases. So on this diagram here, the phases are being represented in blue and yellow, colors that I chose because that's a pairing that's reasonably visible even to most people who are colorblind. But you can use other strategies for showing phase. Oftentimes we'll shade one phase and not the other phase. That gives you really good contrast as well. So these terms, 1s, 2s, 3s, that I'm starting to throw out, how do they relate to those quantum numbers? Why do I know that 1s has n is 1 and 2s has n is 2 and 3s has n is 3? Well, because whenever we have a label for an atomic orbital, let's say I was now talking about a 5s orbital, the number in the front, that is the principal quantum number. That is the n value. And the letter after it, that comes from the angular momentum quantum number. So if L is 0, that will be the letter S. If L is 1, it'll be the letter P. If L is 2, it'll be the letter D. And if L is 3, it'll be the letter F. And you don't need to write all that down because that's coming up in the next few slides. But it is very simple to identify the first two quantum numbers for any orbital for which you're provided the label because they're right in front of you. So p orbitals are up next. They have an angular momentum quantum number of 1, an L value of 1. That means that they have one planar node. And you can see on the diagram in front of you that if we were to stack the 3 possible p orbitals all on top of each other, they combine to make something that is approximately spherical, depending on what percentage cutoff you've chosen for the drawing of your pictures. If this shows 90% or 95% or 99.99999%. Why are there 3 of them? Because if L equals 1, then ML equals -1 or 0 or +1, and that's 3 values. 1 points along the x-axis, so it's called the 2px with a subscript x. 1 points along the y-axis, it's the 2py with the subscript y, and 1 points along the z-axis, it's the 2pz with the subscript z. These stack together because they are orthogonal functions, which is a fancy math word for perpendicular. Just like the s orbitals, if you have nodes left over after that initial planar node because you have a principal quantum number of 3 or higher, there will be radial nodes as well. So then you will have what looks like the shape nested inside a bigger version of the shape, nested inside a bigger version of the shape, as you see in this diagram here. Next up, we have the d orbitals. D orbitals have L equals 2, angular momentum quantum number equals 2, and therefore 2 planar nodes. For 4 of them, that gives you the shape that I drew last video, that kind of looked like a clover leaf or a set of petals on a flower. The 5th one, which is called the dz squared, actually has nodes that look like a pair of cones meeting at the points in the middle rather than just simple flat planes. And you'll see a picture of that on the next page. Similarly, if n is large enough that there are nodes left over after those 2 planar nodes, there will also be radial nodes, and again, you would have the nested cloverleaf within the bigger cloverleaf within the bigger cloverleaf. So what do these d orbitals look like? This is a beautiful computer graphic generated by an artist somewhere and published in a textbook. I can't draw this. If I want to draw the d orbitals, then what I'm going to do is I'm going to make my life easier by drawing them flat and adjusting my axes to make it easier for somebody who cannot draw to still clearly communicate where the nodes are, where the lobes are, and where each phase is. So we have 5 d orbitals. So I need 5 sets of axes. 1, 2, 3, 4, 5. You can see that 3 of the d orbitals have the lobes pointing between the axes. So the dxy has this lobe here that's kind of in the middle of the x and y axes. And here's your dxz showing you a lobe in the middle of the x and z axes, and the dyz here again showing you a lobe in the middle of the y and z axes. And all of the other lobes are similarly located in those spaces. So if I want to draw the shape of the dxy or the dxz or the dyz, I do that, but I kill the perspective. And so I'm going to get something that looks like this. My lobes should not quite be touching the axes, but of course I'm not really artistic enough to show a hair thin border between my lobe and the axis, so I'll just do the best that I can. And since this is the dxy, then the axes that my lobes are between are the x and y axes. For those of you who are mathematically inclined, you can think of this as having nodal planes for which the equation is x times y equals 0. So there's a nodal plane right through the x-axis, and there's a nodal plane right through the y-axis. For the dxz, my picture is going to look incredibly similar. Be clear that that is xz as a subscript, not written next to the d, in that I'm going to have all of my lobes between the axes, almost but not quite touching it, and the axes in question are the x-axis and the z-axis. And again, for those of you who are mathematically inclined and want to think of it that way, the nodal planes are defined by x times z equals 0. dyz, probably not going to surprise you that I draw in the same way again, just by renaming my axes again. So here I have lobes between the axes pointing out into each of those quadrants there, and here I am in the space between the y-axis and the z-axis, and again my nodal planes can be defined as yz equals 0. So that takes care of the top 3. The next easiest one to draw is called the dx squared minus y squared. Why is it called that? Well, because its nodal planes are defined by the fact that x squared minus y squared equals 0 for the nodal plane. And what does that mean? Well, it means that there are nodal planes going exactly along the x equals y. And so therefore, my lobes are going to point directly along the y-axis and directly along the x-axis, and I'm going to get something that kind of looks like that. And then finally, I have the dz squared orbital, which kind of looks like a p orbital pointing up and down along the z-axis, but there's also this kind of donut-like shape around the middle, which is of opposite phase to the top and bottom lobes. If you were to do a perfect cross-section of that, even though you can't see it in this picture, it would still kind of look like a funky cloverleaf kind of shape, because it would kind of come in looking like that. And that's my best attempt to try and draw the dz squared. So that one should look like a p orbital in which the two opposite phases are the same, which of course never happens for a real p orbital, but in this case it happens because there's this extra lobe in the middle that kind of looks like a donut, and the up and down is the z-axis, the left and right can be either the x or the y-axis. Doesn't really matter, because as you can see in that picture, whether you look at your orbital from this direction or this direction, it looks the same. So then that brings us to the f orbitals, which are the last atomic orbitals that can have electrons in any elements for which we have discovered to date in the ground state. I can't draw them, and I don't expect you to be able to draw them. And for that reason, I've included a screenshot from the Orbitron, which is a fantastic little site for playing around with what the different orbitals look like for different sets of quantum numbers. Unfortunately, it's written in Flash and will therefore probably become inaccessible very soon unless they update it. So I grabbed a screenshot just in case it goes away. F orbitals have an angular momentum quantum number of 3. That means they each have 3 planar nodes. So imagine the cloverleaf of the d orbital chopped in half again, which is pretty much what you see for the bottom 4 examples of the f orbital. And then the top 3 kind of look like that dz squared with an extra node through the middle of that. We will be putting electrons into f orbitals. If I gave you a picture of an f orbital, I would expect you to recognize it and go, oh yeah, okay, that's the next one up, that must be the f orbital. But I do not, under any circumstances, expect you to be artistic enough to generate me a picture of one yourself, because if I can't do it, it's not fair to ask you to do it. And those are the 4 shapes of orbitals that are relevant to ground state atoms into which we are able to put electrons. There do exist orbitals with higher values for the angular momentum quantum number, G's and H's and so on, but they are so high in energy that electrons would only ever exist in them in an excited state atom. And so we will not be expecting you to write electron configuration